We're going to look at Langmuir isotherms for binary gas phase mixtures. So the idea is we have two components in the gas phase, and we want to see how much is absorbed on the surface of each component and how this changes as we change the temperature, we change the heats of absorption, or we change the relative pressures for a fixed total pressure. And we're going to do this by looking at a Mathematica simulation that's available in the Wolfram demonstration project website. The location's given here, so I'm going to bring up that demonstration for you. And so what we're plotting here is the number of molecules absorbed per site versus the total pressure, so the sum of the partial pressures of A and B. For the conditions we're showing here, the heats of absorption are the same for A and B, and the pressure of B is twice the pressure of A. And since the pressure of B is higher, then of course more of B absorbs than A. And note that as we increase the total pressure, we start to saturate the surface. We can't put more than one molecule per site for the model we're looking at. And so let's look exactly what the Langmuir isotherm model is. It says the fractional coverage, so the fraction of sites covered with molecule A, are related to an absorption equilibrium constant for A, the partial pressure of A, over 1 plus that absorption equilibrium constant and the pressure of A. If we also have a second component present, then we have an additional term for B, and this assumes A and B each occupy one site on the surface. So now let's go back to the simulation. So we're looking at Langmuir isotherms. The number of molecules absorbed per site is a function of total pressure. Now the heats of absorption are the same. There's more B molecules absorbed than A molecules because the pressure of B is twice the pressure of A. If we're to raise the temperature, we see that the coverage goes down significantly. If we lower the temperature, we'll notice that we reach saturation, so that higher total pressure makes no difference on the amounts absorbed. And in this case, the amounts absorbed summed together correspond to 1 molecule per site. So that's the effective temperature. So let's go back to intermediate temperature. Let's look at changing the heats of absorption. So if I increase the heat of absorption of A, then I can increase the amount of A absorbed relative to B, even though the pressure B is higher. And notice this is a small change in the heat of absorption because the heat of absorption is exponential in this absorption equilibrium constant. And so I can have dramatically different amounts absorbed. So you can imagine for a separations process, if we preferentially absorb one molecule in, say, a pressure swing or a temperature swing absorption process, we can occupy the surface preferentially with the more strongly absorbing molecule. Likewise, if I lowered heat of absorption, we can reverse it rather dramatically in the other direction. And let's go back to the same heats of absorption. If we look at the effect of the relative pressures, when I make the pressures the same, the heats of absorption the same, we have the same amount of each component absorbed. But as I raise the pressure of B relative to A, then I can preferentially occupy the surface with component species B. So the Langmuir isotherms are important in catalysis and in separations. They have a lot of simplifying assumptions. You have to keep that in mind, but they often fit experimental observations pretty well. And so you can, on your own, use this Wolfram Mathematica simulation that's available. You don't need Mathematica to use it. And here again is the location of the simulation for the Langmuir isotherms.